Welcome to the second video in this mini-series about gravity. We previously discussed how objects on the surface of Earth feel a force, a weight, towards Earth's center. In this video we will take this idea of gravitational force and apply it to any two objects, like other planets, using Newton's universal law of gravitation. So what will you learn in this video? You will learn what Newton's law of universal gravitation means and how to use it. You will learn how to derive the gravitational field strength G and calculate it for other objects than the Earth. You will learn why the Earth actually accelerates a tiny bit towards you, not only you accelerating towards the Earth. And you will learn why you weigh less at the equator than at the poles. You already know that at the surface of Earth, the weight of an object is given by mg. But what if you were at another planet? Or what about two objects being gravitationally attracted to each other in deep space? That can be described using Newton's law of universal gravitation, which looks like this. There's quite a few terms in here, so let's break it down. We first have Fg, which is the force experienced by each object in newtons. We then have capital G, which is Newton's gravitational constant, given in meters cubed divided by kilograms divided by seconds squared. Then we have capital and lowercase m, which are the masses of the two objects involved. And we have r, which is the separation between these two objects given in meters. There's quite a few things to note here. For example, there is a negative sign in front of the terms on the right-hand side. This negative sign is only there to remind you that the gravitational force is always attractive. You can never have gravity that pushes two objects away from each other. They always attract each other. You also have an r squared term in the denominator, and this is what's called an inverse square law. It just means that the force decreases very rapidly as you increase the separation between the two objects. So the strength of the force depends on the masses involved and their separation, r. And this gravitational force applies to any two objects in the universe. Every object in the universe attracts every other object. Now, what about the units of capital G, this new gravitational constant? They look quite funny, but there is a neat way to figure out where these units come from. If we do like we did when we derived the units for gravitational field strength, we just rearrange the equation that we have in favor of G. We know that the units of G is then newtons times meter squared divided by kilogram times kilogram. We know that newtons can be rewritten as kilogram meters over second squared. And now we just simplify. And what we get is that the units of G is meters cubed divided by kilogram times seconds squared. Now to a small but very important detail, and that has to do with the center of mass of the objects. The shapes of the objects involved in gravitational force doesn't actually matter. As long as we know the mass of the object and where its center of mass is, we know everything that we need to know to calculate the force. So for example, Earth's center of mass is at the very center of Earth, and James's center of mass is probably somewhere around his belly. And it's between the center of masses that we also measure the separation, r. So we can consider the separated objects as point masses, located at their centers of mass. The shape of the objects doesn't actually matter, as long as we know where the center of mass is. Now, knowing the force that each object feels, how do we figure out their acceleration? Well, we know that the forces are equal and opposite and given by gmm over r squared. You notice here that we have skipped the negative sign, which is because we're explicitly keeping track of the direction in which the objects are experiencing force. So, we can use Newton's second law, Fg equals ma, and equate that with the Fg that we have up on top. And what we get is, of course, gmm over r squared, but we have factored out the m in front. And if we take this m to be the mass of James, we now see that within the brackets we have an acceleration. And this is what James is going to experience as his acceleration towards Earth. if James was standing on Earth's surface, what would R be? Well, if you remember, R is the separation between the centers of masses. So it's between James's belly and the center of Earth, which in the grand scheme of things is about the radius of the Earth. We also know the mass of the Earth, and we know the value of the gravitational constant g. It's always the same, regardless of which problem you're doing. So we can now use all this information to calculate James's acceleration towards the Earth. Can you guess what it is? 9.81 meters per second squared. And this looks eerily familiar. It is actually the gravitational field strength on Earth's surface, as we discussed in the last video. Now, James accelerates towards the Earth at the rate of g, the gravitational field strength. But we also know that the forces are equal and opposite. So James experiences a force downwards, and the Earth should also experience a force upwards. So if we have the mass of James, mj, and the mass of the Earth, me, we know that the Earth will actually accelerate upwards a tiny bit, given by ae in this case. So we can just use Newton's second law and equate the two forces and rearrange for the acceleration of the Earth upwards. And if we plug in the values that we have, the mass of the Earth, the mass of James, which we take to be 80 kilograms, and the gravitational field strength, what do we get? We get that the Earth accelerates upwards at a value of the order of 10 to the minus 22 meters per second squared. And this is, of course, a tiny acceleration, but it is real. The Earth actually does accelerate upwards towards you because of your mass. Now we can use the formula for gravitational field strength, A equals gm over r squared, to calculate the gravitational field strength for other objects. For example, if we take Jupiter, the biggest planet in the solar system, it has a radius of 6.99 times 10 to the 7 meters, and it has a mass of 1.90 times 10 to the 27 kilograms. If we plug those values in, we get a surface acceleration of 25.9 meters per second squared, significantly higher than at the surface of Earth. Also, we can calculate the gravitational field strength on the surface of the Moon, and what we get is a value that's far less than on the surface of Earth, only 1.62 meters per second squared. Now we can also calculate the gravitational field strength on the surface of a football. Why not? So a traditional football has a radius of about 12 centimeters and a mass of about half a kilogram. And what we get is a surface acceleration of 1.99 times 10 to the minus 9 meters per second squared, which is far too little to ever be noticeable by any human being. Now we're going to discuss why you actually weigh less at the equator than you do at the poles. You hopefully all know that the Earth spins around its own axis. It completes one cycle every 24 hours. That's how we get day and night. But this spin actually makes the Earth kind of bulge a little bit at the equator. So it's not actually a perfect sphere, but it has one radius at the equator and one radius at the poles, as you can see on the picture. And these two radii are actually quite different, and they create different gravitational field strengths depending on where on Earth you are. So if you use the formula and the value for the gravitational constant that we have since previously, we can calculate the gravitational field strength at the equator using the value 6.38 times 10 to the 6 meters as the radius at the equator. We get the gravitational field strength at the equator to be 9.78 meters per second squared. And using the radius at the poles, which is a bit less than at the equator, we get the gravitational field strength at the poles to be 9.84 meters per second squared, which is quite a bit higher than at the equator. So how are these differences in gravitational field strength going to influence your weight? Well, we can use the formula that we know, weight equals mg, to calculate this. So for James, his mass is about 80 kilograms. And using the formula, we get that his weight at the equator is 782 newtons. Similarly, his weight at the poles is 787 newtons. So there is quite a bit of a difference in his weight, depending on if he's at the poles or if he's at the equator. And this weight difference is due to the difference in radii between the equator and the poles. There is also another reason why you weigh less at the equator than at the poles, and it has to do with the fact that the Earth spins around itself. If James is standing at the equator, he will spin the fastest, which means that there will be quite a significant centrifugal force acting outwards, counteracting the force due to gravity he experiences inwards towards Earth. So that will result in him weighing slightly less at the equator than at the poles, where he's standing still, essentially. So that's the end of this video, and you should now know what Newton's law of universal gravitation means and how to use it. You should know how to derive the gravitational field strength and calculate it for other objects. You should know why the Earth accelerates a tiny bit towards you, and you should know why you weigh less at the equator than at the poles. If there is anything that you are confused about or that you're wondering, please leave a comment down below or save your question and you can ask me on Wednesday's class. I'll see you soon.